pleasure to introduce Andreas Hartmann for his second lecture of his mini course on interpolation and sampling. Thank you.
Okay, thank you for the introduction, and thank you for coming back to this talk. I don't know what's happening now. Okay, so as I explained yesterday in the second part of the lecture, I will talk about a very classical situation, so interpolation in the Hardy space H2, and I would like to give the proof of the interpolation result. I think I will prove everything except Carlson's embedding theorem. And I feel that this is a quite representative situation for interpolation in a large class of spaces. Okay, here are some reminders maybe from yesterday. When studying interpolation, we need to consider by which class of function or which are the functions we want to interpolate with. And then we also have to ask the question, what are the values we would like to interpolate? And so there were two situations where the answers were quite natural. It was when we look at holomorphic functions which are uniformly bounded. So this is the choice of the class of functions you want to use to interpolate. And then the trace is just the bounded sequences. There's still people arriving here, but it's good because I'm just repeating things from yesterday. And for p equals 2, in particular when we have a reproducing kernel Hilbert space, and again that's the main situation which is interesting for interpolation, because when you interpolate you need to give a sense to values and points, and the value and points make sense if point evaluation is continuous. It's a way of considering the problem. I will call the definition for interpolating sequences. So once we have fixed reasonable sequence space little l, we will say that a sequence lambda of points in the domain omega, in which the space X is defined, the trace of the space is equal to this sequence space. Another way of expressing this is to say that the restriction operator, so which associates to each function f the sequence of values f lambda n, is into little l and onto little l. And so yesterday we saw one half of the proof of this theorem. If you have a reproducing kernel Hilbert space, then sequence is interpolating if and only if the associate sequence of normalized reproducing kernels is a so-called resequence. And I remind that, okay, there's a definition for resequences, but I remind that resequences are, for example, isomorphic images of orthonormal bases or orthonormal sequences. It doesn't really play a role. And also they are equivalent to unconditional bases, which means that you can sum in whatever order you want. Okay, so let me go back to the Hardy space. So yesterday we discussed H infinity, so the space of uniformly bounded analytic functions. But today I would like to focus more on the Hilbert situation, so the Hardy space H2. There are different ways of defining the space. Either you can consider it from Taylor series. Okay, since these are holomorphic in the disk, we can represent it in the Taylor series, which has convergence radius at least 1. And in particular, if AN is L2 summable, then these define the Hardy space H2. It's known that spaces in the functions in the Hardy space admit non-tangential boundary values everywhere. And so you can give a sense to these functions on T, the circle, which is the boundary of the unit disk. And then you can consider Fourier series, and it turns out that H2 is exactly the space of those functions defined on the circle for which the negative Fourier coefficients are vanishing. And then there's, of course, also this definition based on this dilating radii. So if this supremum is bounded, then the function is in the Hardy space. But I won't really use that. In the Hardy space, we have two useful tools. The first is factorization. So there was a course, I think, on Hardy spaces. So this is rather a reminder for those who have followed the course on Hardy spaces. Maybe there are still people who are not acquainted very much with that. So these are some reminders, which of course will not replace a course on Hardy spaces. So factorization means that whenever you take a function in the Hardy space, be it HP, H2, H infinity, in fact, this result is even true in a very large class, which is called the Nevanina class. I won't talk about this. Then you can write the function f as a product of a so-called inner function, which means I is uniformly bounded by 1 in the unit disk, and it takes boundary values of modulus 1 almost everywhere. As I told earlier, function in the Hardy space, they admit non-tangential boundary values almost everywhere. And so f will be the zero-free part, but in a more general setting. So it's zero-free inside the disk and also somehow on the circle. And so this means, for example, you have no function which can go very fast to 0 close to the boundary. Okay, what's interesting, what will be interesting for us later is that, so I is an inner function, it has boundary values of modulus 1 almost everywhere. And then this implies immediately that little f and big F has the same HP norm, which you can see from the formula which is given here. Okay, this we will need in a second. And there's also the reproducing kernel. I've already talked about this yesterday. This is just the Segel kernel. And so this is more or less the Cauchy formula, which explains why f integrated against k lambda turns back the value of lambda. Okay, this should be a lambda here, excuse me. The z here is, of course, a lambda. And also, as I said yesterday, a reproducing kernel, I can compute its norm, which is given by this formula. Inner functions, they can be categorized in two parts. There are Blaschke products, which take the zeros inside the disk, and singular inner functions, which take care of what can happen on the circle. Okay, a Blaschke product, so it's a function which vanishes in points inside the disk. These points, I call them lambda. And in order that this works, they have to satisfy this Blaschke condition. So the distance to the boundary have to be summable. And then this elementary Möbius factor, which you renormalize to make them positive at 0, well, they are multipliable at infinity, so you get convergence of the corresponding Blaschke product. A singular inner function is more or less constructed like an outer function. Instead of putting here the logarithm of the modulus of f dt, you take a singular measure. I take the logarithm of the modulus f here. In a sense, I can write f as an exponential of this Poisson extension, but if I look also at the arguments, then I would get the Herglotz kernel, which I see appearing here. Okay, and it's possible to check that a singular function also has boundary values of modulus 1 almost everywhere on the circle. Okay, these are just some little reminders on Hardy spaces. Okay, so let us look at the necessary condition for interpolation. And here I will repeat an argument from yesterday, and you can say repeating things allowed to plan. I think someone has his mic open. I don't know who. If I take a Banach space, so the result here is quite general, and this is again a consequence of the open mapping theorem, as I explained yesterday. So if my restriction operator is into and onto this little L, which is a Banach space, then by the open mapping theorem, I know that I can solve the interpolation problem in a stable way, which means that I can control the norm of the interpolating function by the norm of the trace. Okay, this is quite reasonable. And now I will do the argument from yesterday now in H2. I could do it in a more general case, but for the moment I prefer sticking to this situation. So for H2 we agreed that the right trace is the little L2 with the weight given by the reproducing kernel, and the reproducing kernel squared, 1 over is exactly 1 minus lambda squared. So as yesterday, I pick a sequence in this little L, so which is a weighted L2 space, which takes 0 in all the points different from lambda n. And in lambda n, I take the value 1 over square root of 1 minus lambda n squared. Okay, all the points are 0 except in lambda n, where it's exactly k lambda, okay, the norm of k lambda. And if I compute the norm in this little L sequence space, then of course I get that this norm has to be 1, because it takes just one value, and which is 1 over the weight. Okay, so then of course I can interpolate this sequence, and by proposition 1, I can interpolate in a stable way. And so the argument is exactly the same as yesterday, except that I have to introduce the weight factor. Fn will now be equal Fn of lambda k is Vkn, and this is exactly the delta nk, so this sequence. And F is bounded by constant. Now by factorization, the function Fn contains a factor Bn. So this is a Blaschke product which vanishes in all the points of the sequence lambda except in lambda n. And some function Fn. And now this is not necessarily outer. So Fn could split into an inner function times an outer function. And I know that the inner function, since it vanishes on lambda without lambda n, well, this contains a factor Bn. And the rest of the singular function, of the inner function, excuse me, I will just put it into the capital Fn, which doesn't change the norm of capital Fn. It's still of the same norm as little fn, because there are only inner functions in play. And this, now I can run the argument as yesterday. I get the weight. The weight is the value of Fn in lambda n. Fn, I can write it as this product. Now F lambda n, I can, for example, write this F lambda n as a scalar product of F. Okay, this, as yesterday, I can write this as F against k lambda n. Okay, the reproducing kernel. Okay, and then by Cauchy-Schwarz, I can bound this by the norm of F times the norm of Kn, and the norm of Kn is 1 over square root 1 minus lambda n, and at the end of the day, I can cancel out this factor. The norm of F is controlled by C. Okay, and so dividing through this C, I get again this. Oh, no, that's not. I get again this Carlson condition, which tells us that the Blaschke product in which vanishes on lambda without lambda n, has to be bounded, uniformly bounded from below by a constant. So the aim of what follows will be to analyze this condition further. Okay. So well, first I don't know if this deserves to be mentioned as a theorem, but okay, it's a result. So the proof is essentially the same as for H infinity. The proof works the same way in HP. So yesterday, Javad, he said, what about the other cases, P? And he's right asking this question. So if you have a reproducing kernel space, often you have P versions, and so then you can copy some of the techniques from the version case to the more general P case, P in general strictly between 1 and infinity, because there can be some things happening for P equals 1 and infinity. Okay, it's called the Carlson condition, which we will discuss in a moment. And I would like to, again, to mention these two results. This Carlson condition implies that you can solve a weak interpolation problem. In H infinity, if you have the Carlson condition, then you can interpolate sequences which are zero everywhere except in one point where it's 1. So you can solve the 0, 1 problem. And here is the explicit solution. And in H2, you can also solve 0, 1, quote unquote, problem. The difference is now that we have to introduce the weight. It's nature, because functions in H2, then they can grow, and their growth is controlled by the norm of the reproducing kernel. And so you can solve also this 0, 1 problem, where 1 is replaced by 1 over the norm of the reproducing kernel. No, 1 is replaced by the norm of the reproducing kernel, excuse me. And here we can also give explicitly the solution, which is given by this function. Okay, Bn here will guarantee that the function vanishes in all the points except lambda n. And in the point lambda n, well, the first factor will be 1, and this will produce exactly the norm of the reproducing kernel. Also, what was mentioned yesterday, we had this B orthogonal family. And so you can check that phi n, this function, is in fact B orthogonal to the sequence of normalized reproducing kernels. Since the B orthogonal exists, so automatically the sequence of reproducing kernels, this normalized sequence, has to be minimal. And it can be checked that it is uniformly minimal, but because the norm of phi n, well, this is essentially given by 1 over b and lambda n, which is controlled by the Carlson condition. Okay, so the Carlson condition guarantees that your sequence is uniformly minimal. Okay, so I said that, okay, we have seen that the Carlson condition is necessary. And we have also seen that we can solve a weak interpolation problem. And as I just explained, this implies that on the Carlson condition, the K, which is I remind that this is the sequence of normalized reproducing kernels. So this is a uniformly minimal sequence. All right, and we will see a little bit later, or in a sense now, one question is, does uniform minimality already imply basisness or resequencity? And I will come back to this question later. Okay, so if you want to show that it's a respaces or equivalently that it's interpolating, then we have to solve two problems. So the first one is we have to show that the restriction operator is well defined. It goes into the sequence space. And if I define this measure here, which is just a weighted combination of the direct measures associated with the points, then this is exactly a Carlson embedding. Okay, so we have to show, does the Carlson condition imply this embedding result? And the second condition is, does the Carlson condition imply the interpolation property. So do we have the reverse embedding? Is the restriction operator also on true? Okay, so let us discuss some geometric characterization of interpolation. And there's an easy consequence, which is separation. And here I have a picture that I should have put already yesterday on my slides. Okay, I draw them a little bit in a bad fashion, but okay. Here it's maybe a little bit nicer. So let's suppose that lambda is satisfies the Carlson condition. Now I want to compute the distance between lambda n and lambda k. And as we have seen yesterday, this metric is defined as the modulus of the Möbius transform in lambda n, okay, with respect to lambda n and lambda k. But this is also an elementary factor of the Blaschke product. And now if I multiply much more Blaschke elementary factors, then I will make this smaller because they are all of modulus less than 1. Okay, so I make the product smaller if I multiply with other factors which are smaller than 1. And at the end of the day, I will exactly obtain the Blaschke product vanishing on lambda without lambda k. And I compute this in lambda k. And according to my Carlson condition, this is bounded from below by a constant which is bounded away from 0. Okay, so this means my sequence is separated in the pseudo-hyperbolic metric. So Rho defines the pseudo-hyperbolic metric. And in particular, this means if I take pseudo-hyperbolic disks, which are defined like Euclidean disks, but I replace the Euclidean metric by the pseudo-hyperbolic metric, they have to be disjoint. The pseudo-hyperbolic metric is a metric. It satisfies, in particular, the triangular inequality. And so at the end of the day, we see that, in fact, these neighborhoods will separate. And as I mentioned yesterday, and it's on this nice picture, if I fix the radius of this pseudo-hyperbolic metric neighborhood, then this is like a Euclidean disk. It's not centered in lambda k. It's a little bit deplaced with respect to the center, but still it's a Euclidean disk, and its radius is comparable to the distance to the boundary. So all these disks have the same pseudo-hyperbolic radius. Okay, this has to be clear. So they get smaller and smaller when you get to the boundary. Okay, so Carlson condition implies separation. And now let me speak about the Carlson embedding condition. So let me do this computation here. So by the Carlson condition, we have just seen that the lambda is separated in the pseudo-hyperbolic distance. Now I will pass through logarithms. And so these b lambda k lambda n, they are bounded from below by delta. Okay, now if I call this x, then I remind you this elementary estimate from first year or second year courses. It depends on where you are. So ln 1 over x, of course, I can write it like this. And when x is strictly bounded away from 0, so between delta and 1, so I get universal constants which depend on delta, so that lambda logarithm of 1 over x is bounded by constant times 1 minus x from above, and from below it's also bounded by another constant times 1 minus x. Okay, so this is just another way of writing 1 over the Blaschke product. Okay, and 1 over the Blaschke product is bounded by 1 over delta. This is the Carlson condition, and now I put ln in front, and I push the ln through the product, which turns it into the sum. And so I have to estimate ln of 1 over b lambda k lambda n, and then maybe I would like to replace the -1 by -2, and I take a 1/2 in front. Okay, and then this whole thing, I will call it x, or this is 1 over x, in fact. And according to the estimate which I have above, I can bound ln of 1 over x by 1 minus x, the constant times 1 minus x. So this inequality with the twiddle means there's a constant, and the 1/2 just comes because I have put a square here. All right, so this is not very difficult. Then we have a well-known identity, which is a direct forward computation, that 1 minus this Blaschke factor squared is exactly 1 minus lambda squared, 1 minus mu squared over this denominator. And so at the end of the day, so if I plug in this expression here, I've shown that this sum is uniformly bounded in n, okay, and the soup of this, I will call it n. Sometimes this is called the invariant Blaschke condition because it tells us that the sum of these terms is uniformly bounded, and the usual Blaschke condition is that instead of the b lambda k lambda n, you just take b of just lambda n, okay? And if this is uniformly bounded, independent on n, so this is called the invariant Blaschke condition. Another condition is this implies quite immediately that if I recall this measure mu lambda, so which is this combination of the direct measures, okay, then I can compute the norm of the reproducing kernel with respect to this measure in the L2 space of this measure. And by definition, this is exactly this sum. And well, we recognize this sum. So this is bounded by n. So what we have just shown, and those who were awake until the very end of the conference yesterday, saw this reproducing kernel test or theories or hypothesis appearing also yesterday. So in fact, we have just shown that the Carlson condition, this condition C, implies so that this sum is uniformly bounded. Another way of stating this is that you have a reproducing kernel test in this L2 space. So in a sense, we have a partial embedding. So we want that H2 embeds into L2 mu completely, but for the moment, we know only that this is true for the normalized reproducing kernels, well, for the reproducing kernels. Okay, so let me go further. Okay, I have to erase. I will introduce this definition. A positive Borel measure is a Carlson measure. If H embeds into this L2 mu, and so this is characterized by a quite elementary condition, and this is a result by Carlson, which I will cite and which I will not really prove. This is the only theorem today which maybe I will not prove. And the characterization is given by these Carlson boxes. So if you have an arc on the circle, so then you take a kind of square. It's not really a square. It's a part of an annulus, which has width, which is exactly the length of the interval. Okay, and then okay, you will call this a Carlson window, and the Carlson measure condition. So it's a Carlson measure condition is this geometric condition, which tells you that your measure mu should not put, well, you should be able to control the mass that you put onto the Carlson box, Carlson window, and it's controlled by the length of the interval. And the famous result by Carlson tells us that under this condition, okay, we have the embedding condition, which means that the sequence, the measure mu is indeed a Carlson measure. Okay, Carlson measures in H2 are characterized by this geometric condition here. Okay, and this is the one which we will use. Just a little remark, this theorem, you can prove it, for example, with you can show that the replacing kernel test, in a sense, implies more or less this using a kind of sure test. Okay, so I recall that the Carlson condition implied this invariant Blaschke condition, or just gives also the embedding for reproducing kernels. And now I pick an arc in the circle, and I want to prove that with this condition, I get the geometric Carlson measure condition. So I have to prove that my measure mu, which is the measure mu lambda. Okay, it's I have maybe defined it here. Okay, the measure mu lambda, which I defined here. I want to prove that with this Carlson condition, I can show that mu lambda is the Carlson measure. So I have to prove the Carlson measure condition. So pick I an arbitrary arc and let Si be the associated Carlson box. And then I will consider the upper half of this Carlson box, which I will call Ti. It's the top half of this box. I can show, and I will explain in a minute why I can make this assumption. It's in fact enough to check it for those boxes which contain in the upper half a point of the sequence. So I have a point somewhere here. Okay, this is my lambda n. Okay. If my point lambda n is here, then of course the distance to the boundary of this point is compared to the length, because it's at most the length of I and it's at least half of the length. Okay, so the first condition is clear. The next condition, this argument condition here is also clear, because lambda n and lambda k, they are in the box. And so if I take lambda n bar and I look at the arguments, the difference of the arguments, it is at most I. So the second inequality here is clear also, maybe even without the twiddle here. And the last condition, 1 minus lambda n bar, lambda k, well, I can do it in 2 steps. The worst case is maybe when lambda k is 1, the modulus, then, well, it's just 1 minus lambda n. And the other extreme situation is when lambda k is on this boundary, but then it's lambda k is 1 minus I more or less. And if I multiply all the things here that I obtain, I can see that it's bounded from below also by this constant. So this equivalence is easy to prove. Okay, then I can show, okay, maybe I should try to do a drawing here. Okay, and if I take a point 1 here, now I look with my microscope, so I zoom inside. So my circle is almost flat. And if I want to compute the distance from here to a point, let's call it Z. Okay, I can compute it also, computing first this distance and this distance. It's essentially Pythagoras theorem, but since I take only 2 directions, all norms are comparable, so the one norm is also comparable. And this tells me that if this is Z, okay, then 1 minus Z, this distance is compared to 1 minus this distance, which is exactly the argument, and plus this distance, which is 1 minus the modulus of Z. And all pieces are now comparable more or less to 1 minus lambda, so I get this condition. Okay, this is a quite easy computation. As a conclusion, now I want to compute the mu lambda. So mu lambda is my, I don't write it here because I won't explain all the details here, but I have to compute mu I of the Carlson box Si. And this is exactly the sum of all lambda k in Si, of 1 minus lambda k. Now, 1 minus lambda n is compared to 1 minus lambda n bar lambda k. So I can divide, and this is compared to a constant, and I raise it to a square. It's still compared to constant. And in fact, this is all comparable to a constant. Okay, this is a constant. Okay, so I didn't change much the sum, the first sum. I just introduced a multiplicative constant, but now I recognize that the sum is bounded by m, and this is just 1 minus lambda n. And 1 minus lambda n is comparable to the length of I. So I'm done, and I have proved that the Carlson condition, so the condition on the Blaschke products, implies the Carlson measure condition. And in case this is not, if you don't have anything in the upper half, okay, well, then I get down in dyadic way, and I do the argument as soon as I meet someone, okay, maybe this one, and this one, and so on. And I run the argument on all these pieces, okay? And at the end of the day, each one is controlled by the length of this, the length of this, the length of this, and all these lengths add up to something which is at most the length of the whole thing. It's a kind of generation argument, but it's here very easy. Okay, so we have shown that the Carlson condition, this on the Blaschke product, implies separation and the Carlson measure condition. All right, let's move on because we want to see more. Okay, so we have shown that the condition C on the Blaschke products implies the Carlson measure condition. Okay, here the measure was mu lambda, and by Carlson's theorem, this implies that mu lambda is a Carlson measure. So I have this embedding. Okay, so this gives an answer to the first question. Okay, this is just a remark. So mu lambda, it's in general, if I don't have the separation condition, if I define, if I have a Blaschke sequence and I associate such a measure, then this defines the Carlson measure if and only if lambda is a finite union of these interpolating sequences. You can also extend it to measures supported on the circle. I will not go into details here. And there's also notion of reverse Carlson measures, which is useful for sampling sequences, but sampling problems, but I don't want to insist on this now. All right, so for the moment, what we have proved is that the Carlson condition implies this embedding, okay, and this uses Carlson's theorem. So we have the Carlson measure property, and what we want to prove now is the interpolation property. So if I take a sequence from the sequence space, then I am in this, I'm a trace of H2. Okay, so as I just said, preceding discussion gives a positive answer to the first question. So let's turn to the second question. So now I take a sequence BK, which is in the sequence space. So it has to be summable with respect to this. So Marcin wants to indicate something here. Marcin? Oh! You have to maybe deactivate your annotation tool. Oh, okay. Except if you want to maybe make some remark. Okay, so we have already met this function phi n, which is the B-orthogonal sequence to the normalized reproducing kernels. And we have seen that it solves the weak interpolation problem. Okay, so we have this condition. And now we define an interpolation operator, at least for finite sequences. Okay, when Vn is finite, which means it's zero except on finitely many points. Then I will introduce this interpolation operator. So I have to introduce this additional factor here because phi n, if I evaluate it only against the reproducing kernel, then, well, I get this factor which comes to the other side. I have to compensate it. Okay, but well, if I write it out, then you get exactly Vn times this function. And this is again like we have seen in the Lagrange interpolation formula. Okay, this is something which satisfies delta nk if z is lambda k. Okay, z is lambda k. Okay, so this is again the same idea, and this implies quite immediately that if V is finite, then I have the interpolation property. And of course, it's in the H2 space because phi n, this function is of course in H2, and a finite combination is still in H2. All right, but now we want to look if it converges, and this is quite nice because we'll use again the embedding property. And how do we do this? We have to compute the norm of V. So let's compute the norm of V, and we will do it by duality. This is maybe an idea which goes back to Shapiro and Shields, who, well, I haven't been very rigorous for the history. So Carlson proved the interpolation result in H infinity, and it was in the beginning of the 60s, and maybe 2 years later. Okay. And maybe 2 years later, Shapiro and Shields, they proved the result in HP, and they used an argument by duality. And it's not exactly the same what I'm doing now, but I think the philosophy behind is maybe the same. Okay, so let's compute it by a duality. And so I integrate, take the scalar product of this interpolation operator against H, and H has to be bounded norm by 1. Okay, so then, of course, I can pull out the sum, I can pull out the values Vn, I can pull out 1 minus lambda n squared, I can pull out 1 over Bn lambda n, I can pull all this out of the scalar product, and then I can use triangular inequality. And I know that 1 over Bn lambda n is controlled by 1 over delta. This is the Carlson condition we had. Okay, and what is remaining after this application of the triangular inequality? So this factor is here, Bn is here, the 1 over Bn lambda n is bounded by this, and all what remains in the scalar product is this expression. Now I use Cauchy-Schwarz, okay, and this produces, luckily, the norm of Vn in the weighted space. And it produces this expression here, which we have now to analyze. Okay, so let's analyze this expression. And in order to analyze this, so we have to compute this Bn k lambda n h. So I have reversed the order. It's not very important because we take moduli of this. I bring over the Bn. It gets a bar sign here. Bn is a Blaschke product which contains all Blaschke factor except B lambda n. Okay, so I multiply by B lambda n, so this will give me B, the entire B, and on the other side I also get B lambda n. So recall that B lambda n is a Blaschke factor. It's of modulus 1 on the circle, so it doesn't affect. It's an isometry on the Hardy space. Okay, so I've done this operation. I'm cheating here a little bit because I haven't taken into account some unimodular constant modulus of lambda over lambda or something like that. Okay, it's not a problem here. B lambda is modulus 1 on the circle. So if I take the conjugation, it's like dividing by it. And if I divide by B lambda n, recall that B lambda is lambda minus z over 1 minus lambda z. So it's essentially lambda minus z times the reproducing kernel. So it absorbs this reproducing kernel, and all what is remaining is this kernel. So it's the Cauchy kernel. Okay, and then I multiply all this by z on both sides. So on the left side, I get z. Again, z is of modulus 1 on the circle, so it's an isometry and it's no problem. And instead of multiplying z on the right, I multiply the denominator by z bar, and then I get, oh, again, the reproducing kernel. And at the end of the day, what I see is that this function is integrated against the reproducing kernel, or 1 minus the reproducing kernel. And this is exactly projection of this function onto a point. Okay, now we are in business because we can run our argument. Again, I recall we were computing the norm of the interpolation operator by duality. Then by Cauchy-Schwarz, we had this estimate. Now, according to what we just computed upstairs, this expression, I can replace it by this expression. And what is nice now is that here, this function doesn't depend on n. Okay, it's just an H2 function because BZ H bar, this is in L2 of the circle, and then I project onto H2. So this is an H2 function. P plus is the Riesz projection. Okay, so I evaluate this function in lambda n. And so that at the end of the day, I get the supremum. Okay, I can pull out the supremum here of the sum, okay, because the sum doesn't depend on the supremum. I can pull in the sum. And so at the end of the day, by the Carlson embedding, I know that this function, well, I can sum it to the square against this weight because I have the Carlson embedding. And so I'm done because this is controlled by the norm of H, which is 1. And this is it. Okay, so this shows that the interpolation operator, okay, I was starting from a finite sequence, and for all finite sequences, I get this estimate, but then of course, since finite sequences are dense in this weighted L2, I can do it for arbitrary sequences, and this operator is bounded. All right, so the previous case is quite instructive. So we have seen that phi n, okay, we have seen now that the Carlson condition implies interpolation. By the theorem from yesterday, this implies that the normalized reproducing kernels are resequenced, and so also the phi n will be a resequence. In fact, they are spaces in the corresponding model space. And now it's clear that this operator is bounded, and it's exactly the operator, it's exactly the interpolation operator. But now from an abstract point of view, if I knew from another way that phi n is a respaces, I could have stated immediately that the interpolation operator should be that. Okay, so if lambda is interpolating, we have seen this implies the Carlson condition. The Carlson condition implies separation in the Carlson measure condition. And we have seen in this setting that the Carlson measure condition or the Carlson embedding was a central piece to prove also the convergence of the interpolation operator. So these objects are not disconnected. And more generally, we can ask if you have separation and Carlson measure embedding, Carlson embedding, does this imply that you have interpolation in the reproducing kernel Hilbert space? And I want just to indicate this result by Aleman, Hartz, McCarthy, and Richter, which is quite recent, in which they gave a positive answer to this question, provided that the space satisfies the complete Pick property. There were partial results earlier by, for example, Bordeaux, etc. This is a summary result, maybe just to recall all what we have done until now. So the interpolating sequences in H2, they are characterized by this analytic condition. Okay, it's on functions. We have a geometry condition, which is separation and Carlson measure condition. You have this condition separation and this invariant Blaschke condition. It's equivalent to separation and this reproducing kernel hypothesis. It's equivalent to this sequence to be resequence, and of course then that the B orthogonal sequence is resequence. It's equivalent to this, and this I haven't shown it really. This I haven't shown it. And you can show also that it works for arbitrary P, and the interpolation operator is quite closely related to that. There's a last slide. I don't know exactly what I'm saying. It's maybe just some remarks. Okay, so you have more or less all the elements to prove the interpolation in H2, and the connection with separation and Carlson measures. And there's a general statement for this by Hartmann and his co-authors. Okay, maybe I want to recall this because I was mentioning this before. In the beginning, I was saying this Carlson condition implies weak interpolation. Weak interpolation tells you that we have uniform minimality of the reproducing kernels. And now we have seen that in this space, it implies also interpolation, so Rees condition. And a natural question could be, does uniform minimality of a normalized sequence of reproducing kernels in reproducing kernel Hilbert space always implies unconditionality? Or, well, you can even ask this question in a more general setting. And there are several positive answers. Of course, in the Hardy space, we have just shown the result. For the Bergman space, Schuster and Seib, they were exploring Hartmann's extremal function, which is the right translation of this Blaschke function. So in this space, the answer is yes also. And for Fock spaces, Schuster and Seib also gave a result in 2000. So for P less or equal to 2, it's still okay. But if you take P bigger than 2, uniform minimality does not longer imply interpolation. Okay, that's all for today. Tomorrow I will speak about Fock spaces, and I will explain how to use debar methods to use an interpolation problem in Fock space. Okay, thank you very much.
Thank you for the wonderful talk. Any questions, comments, suggestions? So there is a question in the chat. Is there a characterization of interpolating sequence for Hardy space on the polydisk or the unit ball? Great question.
It's I don't think so. At least there's no usable definition. Maybe there's some abstract condition. There are many partial results. It's a difficult problem. And of course, between the unit ball and the polydisk, there are quite some differences of geometrical differences. Of course, you can give some sufficient conditions from what has been done here. There are many experts in several variables who have worked on this, and there's some literature on this. But I think there is no definite answer to this question.
Okay. More questions, comments? If not, let's thank Andreas again.
Thank you.